Alright, chapter 13 is acids and bases. Just so you're aware, lots of things around you are acids and bases. Most things are, actually. Let's take a look at a list of some things you'll already know. Probably. Oh, there you go. So common acids are lemon juice, vinegar, protein, so things that are in meat are common acids. Then there's also things like battery acid. Common bases are Windex or baking soda, soap, are all common bases. Soap's actually made with a really strong base that'll get there. But it's used to make your own common soap. Okay, so the pH scale is what we use to measure how acidic, how much acid's in something, or how basic something is, how much base there is. So it generally runs from 0 to 14. Technically, you can go beyond 0 and get a little negative, or you can go beyond 14, but almost all solutions will run between 0 and 14 for a scale. It's a really easy way to compare how strong an acid or base is, how strong a solution is. It's going to be based on how many protons, an H plus we have. So that's your hydrogen atom, which normally, if you guys remember, got one proton and one electron. So it's an H plus, it means it's lost its electron, it's just got the proton floating around there. So how many of those lone protons we have floating in the solution? The more than we have, the more acidic it is. So here's a scale saying really acidic over here, so battery acid's quite strong. Quite basic things are over here, so lye, that's what I talked about, that's what you use to make soap. And then things that are neutral means it's not acidic or basic, it's neutral, it's right in the middle. So things like water, that would be exactly neutral. Human blood is a little bit acidic. I'll talk about later how my blood, as a diabetic, is sometimes trying to kill me because it gets too acidic. Lucky me. Right, so we said the more H plus it's released or given off into solution, the stronger the acid. Some acids give off a little bit, some give off all of their H plus. And so if there's a lot of H plus in solution, that's the lower the pH. So if we go back here, lots of H plus in there, the pH should be down here. If there's only a little bit H plus given off, it'll be closer to the 5 or 6 range. Okay, how do we know if it's an acid or a base or neither? That's a great question. Right, so all acids have to begin with an H in front of it. So if you see HCl, H2SO4, that's an acid. It's called, technically it's a definition of a Bronsted acid, but that's not that important. And they have to donate an H plus if you see them in a reaction. So there you go, HCl, H2SO4, HNO3, they all have that H in the beginning of the reaction. That's what you need to know. Also, other facts you want to know about these, that they're going to turn litmus paper red. So certain types of paper that will react to acids and bases, it's called litmus paper. It's an old saying called a litmus test that would test and show things or prove things. This paper will turn red when you dip it into acids. They also dissociate or break up to create H plus ions, which makes sense, right? If you break apart HCl, you'll make Cl ion, but you also make an H plus ion. So example, we have HCl plus water, they're going to react, and they're going to make this H, they're going to combine with the OH in water to make H3O. So there's actually the H2O here together. This H is going to come over here and make a combined H3O plus, I should say, and Cl minus. So technically, what we say as H plus is technically H3O plus called hydronium ion, but we usually just call them H plus ions or protons. But technically an H plus ion is really unstable. They don't stay on their own. They'll find something to connect to, and water can be that thing. It's usually what it connects to. But for simplicity's sake, we usually just write them as H plus ions. Strong acids are ones that fully break up. So this process goes from starting 100% here to then having all of the HCl turn into hydronium or H plus ions. Weak acids, only like under 5% of this happens. So we make it look like it's just one HCl molecule and one water molecule going here. But you remember, back to moles, if we have a mole of this stuff, it's really 6.02 times 10 to the 23rd of them. That's billions and billions and billions and billions of these particles. So if you got a billion of them, only 5% react. That's not that many. You're only making a relatively small amount of H3O particles. Okay, other facts. It's an acid, it's got to have a pH less than 7. So 6.9 down to 0, or technically it can go a little lower than 0. And acids taste sour. Lemon juice, lime juice, those are both acids. Not very strong ones, but technically if you were to eat a strong acid, it would be sour before it would melt off your tongue, but I do not recommend that at all. Okay, other side, bases. How do we recognize a base? Not like dropping the base, but yeah. Alright, so all bases receive an H plus in the reaction. They're the exact opposite side of this. They're gaining those H pluses that the acids are giving up. And many of them, but not all, have an OH minus in them, or an OH. So they all dissociate, they all break apart to make an OH at the end of the reaction. So when the reaction's done, there will be an OH created by them, even if they don't have an OH in them, though most of them do. Facts about them: bases will turn litmus paper blue. So bases will turn blue. Bases have a pH bigger than 7. And bases taste bitter. So a lot of alliteration here. Bases blue, bases bigger than 7, and bases taste bitter. Examples are sodium hydroxide, magnesium hydroxide, and then ammonia. Here's one that does not have an OH group in it, but still a base. And it'll still form OH minus when a reaction happens with it. So an acid plus ammonia will still make OH minus ions at the end of the reaction. So here's ammonia plus water makes ammonium plus OH minus. That's still happening since this is grabbing an H plus from here and leaving OH minus behind. That shows it's a base. Head up. Okay. Again, so strong bases, like strong acids, dissociate or break apart 100% of the time. So if NH3 was a strong base, all of the NH3 would turn into NH4 plus and create equal number of OH minus atoms or molecules. But if it's a weak base, like it actually is, less than 5% of these molecules will turn into these guys. Okay, technically the most common reaction that keeps your blood's pH level where it's supposed to be, which is actually called homeostasis, keeping a pH level at about, I think it's 7.7, is this guy. So this carbonic acid is sitting in your blood, which sounds horrible, but it's supposed to be there, plus water goes to the carbonate ion plus, the hydrogen carbonate ion plus ammonium, or H+. So we've got this arrow going just one way, and it's kind of, we talked about things so far, that you go from the product, or the reactants to the products. But technically, this arrow could go both ways, and it does. These guys are turning into these guys, and these guys are turning back into these guys. So it's called equilibrium. They'll go back and forth to try and keep your body's pH to where it's supposed to be. If your blood's pH gets too acidic or too basic, too high or too low, it starts to do damage to you. Now, being a diabetic, my body's, when my blood sugar gets too high, it starts to get too acidic, and my body literally is eating away its organs, which is why it causes some of the damage to different organs in my body. Lucky me. So I need to help myself make sure that my pH stays in line by doing a bunch of things. But your body's pretty good at keeping this in track and keeping it close to 7.7. So the more H3O plus in solution, more of this is created, the more acidic your blood is. So my body has trouble keeping this at the right concentration, the right molarity in my bloodstream. Yours is pretty good at that. Most of you. Alright, last thing, we'll look at acids, bases, and their conjugate pairs. So conjugate is kind of like what you talk about in like a foreign language, how to conjugate a verb, how to change it. So an acid is the reactant that donates the H+. We said it usually has an H in front of it 99.99% of the time. The base, oh, there it is, right? H out front. We'll see in a minute that it's the one donating the H. The base is the reactant that receives the H+, and often has an OH in it. Which also the only other reactant. Reactants are on the left side of our equation, if we remember. So that's got to be our base. Now the conjugate acid, this is the product that gained the H. So one of these guys was this guy. So this one looks a lot like this one, but it's missing an H. So it's missing an H, right? This had HSO4. This is H2SO4. So this has one less H. So clearly didn't receive an H, so that cannot be our conjugate acid. This has got two H's and an O. This had one O and an H. So this one has one more H than this one did, so it gained an H. It received an H. That means that must be our conjugate acid. And hey, it was the original base. That also lines up. So that must be our conjugate acid. It was a base, and now it's an acid when the reaction goes the other direction. It's usually a weaker one, but it's still an acid. Because it now has an extra H, it can donate to go the other direction. Our last term, which there's only one thing left, let's make sure that you got it lined up and make sure it follows the same rules. This is the product. Check, it's a product. It lost an H. Well, we said it's got one H here, had two H's here, so that makes sense, and it was the acid. This is the acid. Now it's down to one. So that fits. Awesome. Okay, now you have a try this bottom one. Okay, there's one. Pause it. You give it a shot. Okay, hopefully you're back. Let's see if you got these. There's your acid. There's your base. There's your conjugate base, because it lost the H it had before. And there's your conjugate acid, because it's got an extra H that it did not have before. Now we went the other way. This one could donate an H to this guy to make it turn into this. And this guy would be the base, because it's a one less H than this one had. That's why you can go both back and forth acids and bases. They're all in that thing called equilibrium. Hopefully that makes sense. Not, ask some questions. See you soon.